This is a payload from my latest rocket, and inside there's a camera designed to capture the holy grail of rocket footage. This little Pop-Tart gets loaded into a rocket and sent to Mach 2 using my custom Risky Batman propellant formula, and at Apogee, about 10 kilometers up, we're gonna shoot this thing out the side and have it capture drogue parachute deployment from a third-person perspective. In this series, we're gonna build that camera pod, fill it with electronics and tracking equipment, load that into a custom fiberglass nose cone, put that on top of the guided booster from the Meat rocket, then design a custom N-class rocket motor to fly it, and send all of that to 10 kilometers where the camera will pop out and capture a slow-motion selfie. Then everything will fall to the ground from 10 kilometers and be recovered. Probably. In this video, we're focusing on camera deployment, so let's start testing. The first version I came up with was a hollowed-out 3D printed pod that rode along bearings in the deployer housing. The deployer will sit inside the nose cone with a huge cutout in the side for the camera pod. When the rocket is about to reach Apogee, a servo controlled by the flight computer rotates and releases the pod, launching it out the side of the rocket. If we do this 1 to 2 seconds before Apogee, when the drogue parachutes deploy, the airspeed should be low enough that the camera pod stays stable and pointed in the right direction. The bearings and the screws that hold them in are all plastic and ceramic rather than metal, and this will help the GPS tracker get a clearer signal when the pod is in the rocket. I wrapped a rubber band around the back of it to keep it spring-loaded, then released the pod with this high-torque servo. The first test looked okay, but they weren't that powerful, and it seemed like the pod was tilting to the side a bit. To see how bad this tilt is, I strapped the deployer to my desk to give the pod more airtime on deployment. For these tests to be useful, the pod needs to be mass representative, and I estimate the pod will be about 100 grams with a camera, tracker, and battery to power them both. So I printed these test pods with enough infill to match that weight, then I started testing. For these, I tried a few strengths of spring to deploy the pod faster. This whole shot has to happen in a very tight window of time, so ejecting fast is important. 3, 2, 1. The stronger springs obviously caused the pod to shoot out faster, but they also caused more rotation as it deployed. The camera needs to be pointed back at the rocket here, and if it's tilted too far over, the rocket's not going to be in the shot. And it's not just side-to-side tilt we're getting, it's up and down too. When I started reviewing the footage, I kept seeing the same problem appear over and over. The camera pod pitched downward during deployment. Even when the deployment looks smooth at first glance, once you slow down the footage, it becomes clear that flexing in the deployer was giving the pod a consistent nudge to tilt it down. So if this thing keeps tilting, we kinda have one of two options. Either A, we have to fix the tilt, or B, we use a camera that doesn't care that it's tilted. I'm talking about a 360 camera. Engineers are lazy, we like picking the shortest possible path, and a 360 camera seems like the obvious solution here. In engineering, there aren't many right or wrong solutions. There are solutions that meet the requirements and solutions that don't. So let's define some requirements. We need to eject a camera near Apogee, have it look back at the rocket, and capture the drogue parachute deployment. And that moment happens extremely fast, so the camera needs to be filming at a high frame rate, but still look good, so we should get a high resolution too. And finally, this pod is tiny. We're very space constrained, so I'm setting the requirement that we not use active control systems. Reaction wheels, gas jets, TVC, I've done all these things before, but it's more complexity and more space requirements than we can really afford. To meet all these requirements, a 360-degree camera seems like the obvious choice here. If it's hard to point the camera, why not just capture everything and crop it afterward? Unfortunately, I can't use a 360 camera here because I'm using it as my microphone right now. I don't know, dude. You know what? This joke was way funnier when I wrote the script. I'm on take 12 of this. It's still not funny. Welcome to BPS.space. The engineering is bad and the jokes are worse. Okay, for real, the problem with the 360 camera is that it makes it very difficult to meet both of these last two requirements: high frame rate and high resolution. Recording slow motion video means your camera has to deal with an enormous amount of data. If you're at 240 FPS, your camera has to capture, encode, and record an image 240 times per second. Cameras manage this using heavy compression. Instead of saving a completely new image every frame, they store frames occasionally, then track the differences interspaced between those frames. So we call this interframe compression. That compression pipeline takes a lot of processing power, and that is usually the limiting factor on frame rates and resolutions that your camera can record. It's not really about SD card read-write speed. Past a certain point, it's about the compression pipeline. 360 cameras already have a huge data rate problem because they're effectively recording two different cameras at once. And if you want a comparable resolution once you crop in, you have to film both of these cameras at a much higher resolution. That's why GoPros top off at around 5K resolution while 360 cameras go up to 8 and beyond. Shot for shot, you're not actually getting more resolution, you're just filming a bunch of angles you don't need. Now, some 360 cameras can record at high frame rates. The Insta360 X5 can do 4K at 120 frames per second. That's awesome. That's what my onboard GoPros can do. But the GoPro lens is shooting a 90-degree field of view while the X5 is shooting 200 degrees. I'm simplifying a lot, but once you crop that 200-degree field of view into 90 degrees, your resolution plummets to 1.7K. So we're back to the same problem. To meet all of these requirements, we have to use a single lens camera. And for this project specifically, a GoPro is the right fit. None of these brands are sponsoring this video, by the way, but there's a secret feature inside this that simplifies a lot of stuff. For now, let's get working on a new design. When I slowed down high-speed footage from the early tests, the reason for the tilt started to become more clear. There was slop everywhere. The bearings had play in them, the printed structure flexed under load, and the servo release mechanism introduced a small ramp action as it lets the pod go. All of these imperfections added up to tiny forces that can knock the pod for a loop on deployment. And speaking of deployment, I didn't just want to leave a huge hole in the side of my nose cone. Aerodynamically, that would be a mess. So the first design here used a small spring-loaded door that would open just before the pod deployed so that the outer surface was smooth during ascent. This was made using machined acrylic, but I quickly changed this approach. I publish update videos on Patreon every 2 weeks, and as I was developing this, two suggestions stood out to me. First, I got feedback that the door was unnecessary. If it didn't open all the way or didn't open at all, that's a really dumb way for this thing to fail. Eventually, the simpler solution was to make the door a part of the camera pod itself, but we'll get there later. The second piece of feedback I got was that I probably didn't need the bearings, especially if they're causing a lot of slop. Call these bearings AI the way they produce slop. Anyway, let's fix this, and I'm gonna do that using the sponsor of today's video, Onshape. For the next design, I ditched the bearings and let the pod ride on the inside surfaces of the deployer. The deployer doesn't just hold the pod though, it also holds two flight computers on either side. These are a primary and backup computer, the primary batteries on the bottom and the backup batteries on the side. The deployer also has two slots for screw switches, which I'll use to turn the computers on when it's in the rocket. I'm gonna get this thing on my 3D printer, and while that runs, let me do a cheeky sponsor segment. Onshape is the CAD platform I'm using here, and I've worked with these guys for a long time because of how much I like the product. This whole program operates in your web browser, and it is snappy, responsive, and easy to use. You don't need a fancy machine to run it, you need anything that connects to the internet. I don't know if they can work on your Samsung fridge, but like tablets, phones, computers, anything. If you've seen me talk about them before, you can probably recite this by heart, but let me hit you with some classics. It's a professional grade CAD and PDM system. It's in the cloud, which means it's stupidly easy to work with teams and multiple people on the same design at the same time. Using it will dramatically lower your IT costs as a company because Onshape handles all of that. But what if something breaks? Who cares? Because Onshape pushes updates every 3 weeks. That's right, when they have a new feature, they don't sit on it for a year to publish it next March, they publish it when it's ready. Every 3 weeks. And speaking of new features, Onshape just rolled out MBD, or model-based definition, so you can define tolerances and all sorts of manufacturing info within your parts themselves. Datums, weld symbols, shareable MBD views so your manufacturer can understand exactly what your part needs to do. You can even send them a viewable link of your model. Think about how much better that is than just a drawing alone. This is one of the many big updates for Onshape in the last year, and if you want to give Onshape Professional a shot for free for 6 months, you can do that using the link in the description. Thanks a ton to Onshape for supporting me for such a long time and sponsoring this video. And I think my print is about done, so let's get back to it. I started by experimenting with ways to make these internal surfaces smoother. The less friction there is, the less the camera should tilt. I tried lining the interior with aluminum tape, but the results here weren't great, so I removed that and tried lubricating it so the pod could slide more cleanly. My first attempt here was to use industrial super lube, and this, 3, 2, 1. Oh, wow. Let's try that again. 3, 2, 1.
Wow!
This didn't work well because Super Lube is really thick, but Slideway lubricant, the stuff that I use on machine tools, worked much better. This lube is much thinner, and I found that if I loaded the pod by pushing it in and out a bunch, that movement made most of the deployments fairly straight, or at least straight in the sense that it didn't tilt to the side.
Okay, a little bit of tilt. These are pretty straight.
I don't love how easily dirt and hair can get stuck in this though, and you gotta imagine that if I'm doing this in the desert, there's a lot of dust out there. Plus, while it's nice to know that this motion seemed to improve the results, it just doesn't inspire a lot of confidence in the design that I have to do this weird, whatever this is. And here's the thing, even if I can keep it clean, we still have this downward tilt, so I haven't even really fixed the problem. The downward tilt suggests that the last point of contact between the pod and the deployer might be introducing torque as the pod exits the mechanism. Think of it in the last millisecond of deployment. The camera may be completely straight, but just as it's about to lose contact with the deployer, whichever surface touches the deployer last is going to impart a torque on the pod, spinning it. Since gravity is acting down on the pod, the last surface is usually going to be the bottom of the camera pod, so as it leaves, there's a little friction at the back that tilts it down. I think I have a way to fix this, but in the meantime, there is a big issue I've been ignoring. Capturing footage of deployment is only half the problem. The other half is getting the footage back. There are a few ways we could do this. We could try transmitting video from the pod to the rocket and the rocket to the ground, or from the pod to the ground itself. But both these options massively increase complexity and power budget. Another idea could be to tether the pod to the rocket so that as the rocket falls, the pod stays with it. This is easier for sure, but I'm not convinced it's the right approach. You need a rope that's strong enough to not break if it tangles on the way down, but compliant and loose enough that it doesn't influence the tilt of the pod as it deploys. Any kind of tether is going to introduce little torques into the pod, and as I'm quickly finding out, little torques are a big problem. The most interesting option for recovering footage, and probably the dumbest, is to shoot the pod out. And that's actually it. Just let it fall from 10 kilometers. I'm not kidding. No parachute, no tether, just a GPS tracker in a dream, baby. We'll store the video on the camera's SD card and recover the pod after flight. The camera will also get a lot of structural reinforcement around the card to prevent it from cracking on impact. Now, I have had some pretty bad experiences with cracked SD cards in rockets. I've learned the hard way on multiple occasions that if the card is cracked, it's gone. There's no hope for recovery. So it would be pretty reasonable to say, Joe, you obviously haven't learned your lesson. It's gonna hit the ground, crack the SD card, and you're gonna be sad. Look, before everybody freaks out, let's just run the math. My bet is this thing will spend most of the fall tumbling, so if we take the area from each of the 3 axes and find the average between them, we get about 5 square inches of exposed area. Using that to estimate terminal velocity with a mass of 100 grams, we should hit the ground at about 20 to 25 meters per second, like 40 or 50 miles an hour. That's fast, but it's not like crazy fast. Like if it hit you on the head, it would hurt, but it probably wouldn't kill you. You know, a few months ago I did a video where I said a gallon of milk hitting you at 50 miles an hour probably wouldn't kill you. I just want to revise that. I think it might. In any case, this is why we have bunkers. You calculate the ballistic descent time of whatever you're flying, and you stay in the bunker until after that time. As for finding the pod after the flight, we're going to use a GPS tracker, and that tracker must work. Rockets are already hard enough to find in the desert, and most rockets are large and have big, bright parachutes. The camera pod has no room for a parachute, and it's tiny, so whatever tracker we use must work. Luckily, my friend Ulysses has a company called Silicdyne, and it's the same company that makes the Fluctus flight computer I've used before. This summer, he hit me up about a new tracker that he calls Reprix. It's a LoRa-based GPS tracker with an onboard IMU that allows it to dead reckon and estimate position even if the GPS signal drops out. This thing rocks, it's super tiny, and we're going to talk more about it later. So now that we've got the recovery part covered, let's refocus on the tilting after deployment. From what I can tell, the issue stems from little torques that happen right at the end of deployment. As the pod is bouncing around when it deploys, whatever surface gets hit last will impart a torque. So to control where the torque's from, I added small chevron features on the pod so it only contacts the deployer at specific locations. The idea is to reduce the contact area and make sure the final forces act closer to the center of mass. With these 4 chevrons, I noticed that deployments were a lot more straight and didn't tilt from side to side. But I still haven't fixed that downward tilt. I kind of figured this might happen. I mean, we're still dragging the bottom along the deployer, so we're still getting that, gravity-induced downward tilt. It's not surprising the tilt is still there, and I prepared for this by printing a version of the pod with only 2 chevrons on the side. Since they run right along the center of mass, the last surface that touches the deployer as the pod leaves shouldn't create a downward torque. It turns out, though, this actually made the results worse. It seemed like, without all 4 chevrons, the pod had a tendency to bind up during deployment, which makes it tilt even harder. I went back to having all 4 chevrons, but was still confused about what exactly was going on with the downward tilt. So I turned the deployer upside down to see how much gravity was really influencing the situation. In theory, if gravity is causing this downward tilt, when we put this thing upside down, we should continue to see a downward tilt, just in the other direction now. This only made things more confusing, because in many of these tests, I found that the pod deployed suspiciously straight. So whatever component gravity was playing here, it was getting canceled out when the deployer was upside down. I mean, it's almost like there's an issue I mentioned earlier that I didn't solve yet. This thing is clearly sensitive to really tiny disturbances, little torques all over the place. A torque is just a force offset by a distance, and even if that force is tiny, with enough distance, you can turn anything. That's why if a bolt is stuck, you just make the wrench longer until it's not stuck. And if that doesn't work, the bolt can't be stuck if it's a liquid, but that doesn't really help us here. We can use this distance thing to our advantage by going in the opposite direction. The smaller the distance, the less the torque. And if we drive that distance to 0, by definition, there is no torque at all. So what if we push the pod through the center of mass? For my next attempt, I'm going to redesign the deployer so the spring force pushes directly through the center of the pod. A rod runs through the center of the deployer, and a spring around that rod pushes the pod straight out. Since that spring is the only thing acting on the deployer, and since it's pushing through the center of mass, we by definition should not get torques here. We've eliminated almost every source of tilting on deployment. In theory. In practice, though, the pod still bounced around during deployment. The 1/8-inch rod wasn't stiff enough, and even small disturbances were enough to make it rotate. The 1/8-inch rod not being large enough is more of a design problem than a conceptual one, but we're still also getting torques from the servo releasing the pod. I never really fixed that issue. The way this is currently set up means that the whole assembly bends as the pod is held back. There are certainly ways to design around this, but I think it might be worth zooming out a little bit. One of the requirements I set for this project was to not use active control. I didn't want to deal with the complexity of a reaction wheel in such a small space, because it wouldn't just be 1 wheel, it would be 2 at minimum, maybe 3. We're really space constrained here, but at this point, I have to admit something important about the design. It doesn't work. Admitting your design doesn't work is a very important skill in engineering. It allows you to pivot and change it instead of put your head in the sand and do nothing. I've spent a lot of time and effort trying to make this pod deploy passively stable, and even the tiniest torques are knocking it off axis. Rockets are a really dynamic environment. Maybe I should take the hint and realize that I'm never going to get the perfect environment or perfectly straight deployment. These forces aren't going away, and we can't increase the moment of inertia. That would require making the pod physically larger or heavier, and neither of those options work. I can't really make this cutout larger without serious structural concerns, and going heavier would cause the pod to hit the ground much faster, so I just can't increase the moment of inertia. But what if there's a way to fake a higher moment of inertia? What is actually happening with these torques is that they're changing the angular momentum of the camera pod. As we talked about in this video, angular momentum is the moment of inertia times the spin rate. If we want to raise the angular momentum, but we can't change the MOI, there's only one knob we can turn: spin rate. Oh my god, that's a good pun. I should have written that in the script. All right, never mind. You come to BPS for bad engineering and jokes that are kind of mid. This little piece of brass isn't a reaction wheel, it's a gyroscope. The difference is that this wheel doesn't change speed, it just spins as fast as it can, increasing the angular momentum of whatever else it's attached to. If little torques keep knocking this pod for a loop, by increasing angular momentum, we end up with a semi-active stability that never requires a full control system. This is the same phenomenon that happens with a fidget spinner. This little guy is very easy to rotate until you get him spinning, at which point the angular momentum has increased, so it's much harder to rotate it. There's also some gyroscopic precession here, but we're going to ignore that for now. I mounted this wheel to a simple DC motor inside of a test pod with weights to match the expected mass. Then I threw it in the air to give it a test. The difference in stability between the wheel being on or off is immediately noticeable. The wheel isn't perfectly centered in the pod, so some tests end up with a bit of a nutation, a sort of oscillating corkscrew. I don't really care about this though. The pod doesn't necessarily need to be still, it just needs to point in the general right direction, and with this wheel, it seems like that's the case. And the motor and wheel only add about 40 extra grams to the camera pod, so it's not like we're gonna hit the ground that much harder. Probably. This doesn't mean the stability problem is solved, yet, but it does suggest an interesting middle ground between active and passive stability, sort of a semi-active approach. So next we need to test whether the pod actually stabilizes during deployment. We gotta program the GoPro so it records automatically during flight. We gotta verify that the GPS tracker works, and then we gotta finish building the rest of the deployment system. If you're impatient like me, you can get all that testing footage right now on the BPS Patreon. As I said earlier, I publish videos every 2 weeks for behind-the-scenes updates of what I'm working on in real time. That's how this project is supported financially, and I am so grateful to the folks who choose to support over there. I'm also grateful to you for watching, and I'll be back with another video real soon. I'm Joe Barnard. May your skies be blue and your winds be low. Goodbye.